Let us start the lecture, and the topic of today's lecture is generating functions. Recall that we consider the following random walks. So we add independent, identically distributed random variables everywhere except of some finite set that we call a membrane. So here the jumps may have another distribution. When you exit from the membrane, again you have you have a random walk with independent, identically distributed random variables with some distribution psi. A week ago, we calculated some probabilities for unperturbed random walk. And that random walks were very simple. We jumped up with probability P, we jumped down with probability Q. Well, and to find some probabilities, we used some binomial coefficients, some combinatorics, and it's obvious that if psi is arbitrary discrete random variable, then certain probabilities, for example, that you start from x and finish at y in n steps, can be not calculated explicitly. When I say calculated explicitly means that there is no nice, beautiful formula or probability that, for example, maximum of random walk or minimum random walk is greater than certain number or smaller than certain number. They cannot be, there are no nice formulas. However, sometimes in probability theory, it's easier not to calculate probabilities and expectation or something or distribution itself, but to calculate some transform of the distribution of a random variable. And there are three popular transforms. The first one is characteristic function. And it's expectation of e to the power I z psi, where I is square root of -1 and z is real number. Or sometimes it's easier to work with Laplace transform if random variable psi is non-negative. Then the Laplace transform is defined by expectation e to the minus lambda psi, where lambda is positive number, and here that is real number. And today we will discuss so-called moment generating functions. Of a random variable psi, whose values are natural numbers or zero, so non-negative integers. And moment generating function is defined as expectation s to the power psi, where s, the absolute value of s is less than or equal to. As you may know that characteristic function or Laplace transform or moment generating function determines distribution of the random variable uniquely. Well, and I write here lambda greater than 0 because this function is defined for positive lambda. So e to the power minus lambda xi is less than or equal to 1 if xi is non-negative. Well, and if s is less than or equal to 1, then s to the power xi is also bounded random variable. So all these objects are well defined. Okay, now let us start with rigorous definitions and some important examples. At first, we start with a sequence of real numbers xn, and generating function of this sequence is a function of the form. So generating function of sequence xn is the following series sum axn s to the power n and from 0 to infinity. We will consider sequences such that radius of convergence of this series is greater than or equal is greater than 0. Let me recall you well-known fact from mathematical analysis that the radius of convergence is 1 divided by upper limit as n tends to infinity square root, not square, root of power n of absolute values of xn. So we will always assume that r is greater than 0, and we will consider this generating function for s that are less than r. Well, this is nothing but just Taylor expansion of function x of x. And let's consider a few examples. The first one is this. Assume that xn is 1 for all n positive. What is x of s? So it's a sum 1 plus 1 times s plus 1 squared times s squared plus so on. Okay. Please recall me what is the formula, what's the answer, Igor?
1 divided by 1 minus.
Yes, this is geometric series and the radius of convergence is 1. Another example. Assume that x of s is e to the power s. And the question is how to find the sequence xn. Matvey?
Sum of power divided in factorial.
Yes, so xn is 1 over n factorial. We know Taylor expansion of the exponent. And let me recall you that xn in all cases is coefficient of Taylor expansion, so it's n's derivative of x at the point 0 over n factorial. So if you know xn, then you can calculate its generating function x of s and vice versa. If you have generating function x of s, then xn is determined uniquely. And it's clear that, for example, if you have two sequences xn and yn, and you construct here generating function x of s, y of s, then generating function of sequence xn plus yn is x of s plus y of s, so we have linearity, and if you multiply x by some constant alpha, yn you multiply by some constant beta, then the moment generating function is alpha x plus beta y. So this is obvious. And now let's discuss generating function of a random variable. We assume that xi is a random variable that take values in the set of non-negative integers. Is a random variable such that discrete probability that size n is Pn, so its distribution is this, where sum of Pn is 1. And Pn are non-negative numbers. The generating function or moment generating function of xi is the following function. I will denote it by pxi of s, and the definition is pxi of x is some Pn s to the power n. So the generating function of xi is generating function of this sequence. On the other hand, you may see that this sum is sum of probability xi is n times s to the power n, probability times value, so this sum is expectation of s to the power n. If absolute value of s is less than or equal to 1, then absolute value of s to the power n is less than or equal to 1. We know that sum of Pn is convergent, so we know that the radius of convergence is at least 1. So this function is defined for s between -1 and 1, and maybe even in larger interval. We will consider generating functions for s between -1 and 1, or sometimes between 0 and 1. It's easier. Okay, properties. The first property is the following. If s in 0, 1, then pxi is non-decreasing, non-negative for this s. Well, that's clear. Second property. We know that Taylor series are infinitely differentiable inside the interval of convergence. So pxi is an infinitely differentiable function in the set -1 and 1. I don't know what about -1 and +1. The third property, pxi of 1 is 1. Indeed, pxi of 1 is sum of Pn times 1 to the power n is 1 by the definition. Okay. These were just trivial properties, but And sometimes we know the generating function and we want to make some conclusions about the distribution. And the next property is the following. If xi1 and xi2 are independent random variables, well, and we assume that they take values in the set of non-negative integers, then the distribution, the generating function of sum is equal to product of generating functions, okay, for s less than or equal to 1. If I forget to write this, then I have to remember that I consider only s in this set. Well, the proof is simple. Just let us apply the definition. Generating function is expectation of s to the power xi1 plus xi2 equals expectation of a product. And since these two variables are independent, then you have product of expectations. And then you notice that, okay, this is random. This is generating function of xi1. This is generating function of xi2. So the property is proved. Well, and of course, you know, you have uniqueness. So if xi1, if generating functions are equal, then random variables have same distribution. Let me write here like property 0. So if is equal to this, then the distribution of xi1 is equal to the distribution of xi2. And this follows from this property because you know how to find this probability by differentiating of these generating functions. Okay, this is just basic properties, and let us look at this property more carefully. What is the distribution of psi1? So let us find the distribution of psi1 plus psi2. It's a sum of all possibilities. So psi1 is k and psi2 is n minus k. Recall that psi1 and psi2 are integers and non-negative. Now we use independence and we write this formula as this. K from 0 to n, probability that psi1 is k, probability psi2 is equal to n minus k. And sometimes this formula is called a convolution of sequence. Probability psi is k and psi2 is n minus k. Let us return back. Okay, let us consider general case and assume that you have two sequences xn, yn, that you have a generating function of this sequence. You have a generating function of sequence y, We assume that radius of convergences are positive, and let us discuss what is a sequence that corresponds to product x and y. I will make just formal calculations, and however, everything can be just justified, and there are some theorems in mathematical analysis. Okay, so let's find a sequence Z such that this product is equal to this. So we wish to write Taylor expansion of the product. And let's write X as this sum, Y as this sum, and formally multiply these two series. Okay, the first, okay, it's equal x0 times y0, so we multiply this by this, plus s multiplied to some number. So how can we obtain s? Like x0 times y times s, or x1 s times y0. Plus s squared. How can we get s squared when we multiply these two series? X0 times y2 s squared plus x1s y1s, or x2 y0, plus so on. And let me write down the nth term, x0 yn plus x1 yn minus 1 plus so on, plus xn y0 plus etc. So conclusion is the following, that n is equal to x0 yn plus x1 yn minus 1 plus xn y0. And the sequence Zn sometimes is called a convolution of sequences x and y. Zn is a convolution of sequences xn and yn. So you add all products where sum of indices is equal to n. And I would like to recall you one more time that here we made formal calculations. However, there is a theorem in mathematical analysis that says that if you that you can do this. Okay, and now a few examples. Assume that Xi has a Poisson distribution with parameter lambda. That is probability that Xi is n is equal to lambda to the power n over n factorial times e to the power minus lambda, where n is non-negative integer. Let's calculate its generating function. So we have to consider sum probability times s to the power n, and we simplify this expression. So lambda n to the times s to the power n is lambda s to the power n over n factorial. And what is the answer, Igor?
To
Excuse me, I don't hear you.
it's the sum is power lambda s.
Yes, e to the power lambda s times e to the power minus lambda. So the answer is e to the power
Lambda s minus 1.
yeah, yes. This or plus lambda s minus 1. Yes, correct. And the next example is this. Assume that xi1 has Poisson distribution with parameter lambda 1. Xi2 has Poisson distribution with parameter lambda 2. And the equation is, and assume that they're independent. The question is, what is the distribution of xi1 plus xi2?
Um,
Gennady, do you know the answer or the way how to solve this problem?
No.
Oh, I'm sorry, I don't hear.
I think no, fortunately.
Okay, Matvey, have you any ideas? Vadim?
Well, we know that it should be the distribution of the sum.
Yes.
It's again the Poisson distribution with the parameter lambda 1 plus lambda
And
2.
how to prove it? How to prove it?
We know that to a sum of independent random variables, its generating function will be the product of.
Okay, yes, excellent. So let's calculate generating function of a sum. We know that generating function of a sum is product of generating functions. And we know the formula.
So we'll get lambda 1 plus lambda 2.
Yes, 1 minus s times another generating function. And after simplification, we see that generating function has the following form. And now we look here and we see that, oh, this is generating function of a Poisson distribution with parameter lambda 1 plus lambda 2. And we know uniqueness, that the distribution is determined uniquely. So xi1 plus xi2 has Poisson distribution with parameter lambda 1 plus lambda 2. And this is important fact that you have to know. And you see the application of generating function is very useful, was very useful here. So the proof is just 2 lines. Well, you may solve this problem directly, just calculate these probabilities and write that this probability is equal to this sum, and then plug here the probabilities and then find the sum and so on and so forth. This way is also possible, but I think it's longer. Okay, and now let us discuss the next property number 5. that if you know characteristic function, then you can calculate the moments of a random variable, for example, its expectation. But at first, let us calculate derivative of moments generating function, at least formally. And we know that the moment generating function is differentiable for s between -1 and 1. We know that derivatives are okay. There are it's infinitely differentiable in this interval. We don't know what about boundaries -1 and 1. We know from mathematical analysis that you may interchange derivative and sum inside the interval of convergence. So we don't know what happens in boundary in the boundaries. S to the power n prime times n times s to the power n minus 1. Well, if n is 0, then this is 0. It's just 0. And we see that this is again expectation of psi times e times s to the power psi times s to the power psi minus 1. So value is n times s to the power n minus 13. So probability times value. Or the formal calculations is this. You wish to differentiate s to the power psi. You apply certain limit theorem, say Lebesgue-dominated convergence theorem, and write s to the power psi prime, and you differentiate this, and derivative of this is psi s to the power psi minus 1. So if you forget the formula, just make formal calculations, and this is okay. The answer is expectation psi s psi minus 1 s less than 1. Well, if you calculate the second derivative, you do the same calculations. You differentiate Taylor series, and if you take k derivatives, then the answer is this expectation. You differentiate this with respect to s, then you obtain psi, then psi minus 1, psi minus 2, psi minus 3, and so on. Psi minus 1, psi minus k plus 1 times s to the power psi minus k. And the interesting fact is that differentiating, you may calculate expectation of psi. We are differentiating the generating function, and the result is the following. So let me write like theorem. Derivative exists if and only if there is a derivative of moment generating function at 1. Let me write here 1 minus. Well, I don't know whether generating function is defined for s greater than 1. And the statement, but I know that generating function is well defined for s is less than 1. So this is left derivative at the point 1. And when I write here exists derivative, this means that the limit exists and is real number, so not infinity. And expectation is infinite if and only if this derivative does not exist and the corresponding limit is plus infinity. Moreover, if this is true, then expectation of psi is equal to derivative of characteristic function at point 1. Okay, I have to write minus, but I will not. And formal calculations are simple. Just plug here s is 1. On the other hand, we have to think how to prove this rigorously. We know from mathematical analysis that this is true for s strictly smaller than 1, but what happens for s is 1? If you consider this formula and send s to plus 1 from the left, you may see that this function is monotonous in S. So, and these random variables are non-negative. So by monotonous convergence theorem, we know that the limit of expectations is equal to expectation of a limit. Moreover, this is true even if at least one of these values is infinite. So if you write here, if you think here that this is left limit of derivative, then the theorem is already proved. On the other hand, there is a theorem in mathematical analysis, and by the way, all coefficients in this expression are non-negative, that the limit of a function, the limit of derivative from the left, or the limit of Fourier of Taylor series from the left is equal to the value of Fourier series at the endpoint if coefficients are non-negative. And okay, so this is result for derivative, and you may calculate second moment, third moment, variance, and so on and so forth. Similarly, let me just write formal expressions. And the corresponding statements mean that if at least one side is well defined, then the other side is also well defined. So what is k derivative of generating function at 1? Okay, plug here s is 1, so it's expectation of xi minus 1, xi minus k plus 1. In particular, if we consider second derivative, then you obtain expectation of xi minus 1, or expectation of xi squared minus expectation of xi. And the question is how to calculate variance. Okay, so this is important formula, and another important formula is formula for variance. It is expectation of xi squared minus expectation of xi raised to the second power, and is equal to, okay, look, we know that expectation of xi squared is equal to second derivative plus expectation of xi. And we know that expectation of xi is the first derivative, so plus first derivative at 0.1. And we have to subtract expectation squared. Expectation is the first derivative squared. Well, that's all. So this is formula for variance. And if you forget this formula, don't worry. Just differentiate generating functions twice and recall this formula, and probably that's all. So questions? Okay, if no, let us continue. And the next interesting problem or property is the following. Assume that xi and eta n are non-negative integer valued random variables. So eta n are ID. And we assume that xi is independent of the sequence eta n. Let us consider the following random sum k from 0 to xi eta k. Such constructions appear, for example, in branching process theory, or maybe in physics or in economics. For example, the interpretation is the following. The number of customers during one day is xi. And eta k is amount of money that spends k's customer. So the total profit that you get, and we are owners of a supermarket, is amount of money of the first customer plus second, third, and so on and so forth. Well, excuse me. Let me write k from 1. And if there are no customers, then we say by definition that sum k from 1 to 0 is just 0. And the result is the following. Generating function of a random sum is equal to composition of generating functions pxi and p eta of s. And if you know distribution of psi and distribution of eta, you can calculate this. And via differentiating, you can calculate expectation of random sum, variance of random sum, and other moments just differentiating this composition. So I'll give you two proofs of this theorem. The first one uses conditional expectation. Okay, if we know that psi is non-random, then generating function of a sum, of non-random sum, of independent random variables is just a product. Is just a product. However, psi is random variable, so let's consider the following formula. So we take conditional expectation of this with respect to sigma algebra generated by psi, and we know that expectation of a conditional expectation is equal to expectation of a random variable. Okay, now the second question is how to calculate this conditional expectation. At first, let's calculate the following conditional expectation given psi is n. And it's clear how to calculate it. So if psi is n, then this is nothing but
I think we lost.
I'm
S.
sorry. Yes,
S to the power.
s to the power. Yeah, it was a mistake. So s to this power, s to this power. Yes, s to the power k from 1 to n eta k, and this is generating function of psi1 eta 1 plus eta n, and it's equal to product of generating functions. And random variables eta 1, eta 2, eta 3, they have same distribution, so it's p eta of s raised to the nth power. And if you know this, then this conditional expectation is equal to this, but you have to replace n with psi. So expectation of p eta of s to the power psi. So these are facts. These are known facts from probability theory. However, that they're quite intuitive. And now, second step, denote p eta of s by z. So this expectation is expectation of z to the power psi. And what is this? This is generating function of psi at point z. And now we recall that z is p eta of s, so p psi of p eta of s. Well, you have to be a little bit careful here. This formula is true if n is 0. So you have to remember about this agreement. However, everything is okay. Everything is okay. And by the way, all expectations here are finite if s is less than, if absolute value of s is less than or equal to 1. For example, here, p eta of s is a generating function. If s is between -1 and 1, then p eta of s is also between -1 and 1. So everything is well defined. And I know that students do not like conditional expectations. So let me give you a second proof. And the second proof is the following. Psi eta k. Let's notice that 1 is equal to sum of indicators. Psi is n. So the sets psi is n are disjoint. And indicator is 1 if psi is n, and 0 is if psi is not n. Actually, in this sum, there is only one item that is equal to 1, and all other items are zeros. And let me rewrite this as expectation s to the power sum k from 1 to psi eta k sum indicator psi is n. So this is just 1. And move this infinite sum outside of expectation. Actually, this is infinite sum, so we have to apply a certain theorem. And you may apply Fubini's theorem and check its conditions. And if you do this, you will see sum k is 1 to psi eta k indicator psi is n. So this indicator is 1 if psi is n and 0 otherwise. So you may write here n instead of psi, and you will obtain the same value. So let's do it. Okay, let me write here n. And now observe that this depends only on eta, and this depends only on psi. So they're independent random variable. And expectation of a product is equal to product of expectations because of independence. So expectation of s to the power sum of eta k's and times expectation of indicator. And this is generating function of a sum, and we know that this is product of generating function, so generating function of eta to the power n, and here expectation of indicator. Gennady, what is expectation of indicator?
Well, just probability that
Yes,
psi equal n.
exactly, just probability that psi is n. And now we arrive to to this formula. Probability times value. So the sum is equal to expectation of p eta of s to the power psi, and we denote again z is p eta of s, so expectation z to the power psi is generating function of psi of z, and then we recall that z is p eta of s, and the theorem is proved. The simple corollary is the following. Expectation, let's calculate expectation of this random sum. And the answer is just product of expectations. And actually this formula is very intuitive, how to calculate the average profit if you have Xi clients, Xi independent clients, and the distribution of money that a client spent in a supermarket is at just average number of clients times average profit. So this times this. And proof is simple, just differentiate. So we know that this equals derivative of generating function at 1. And derivative of composition is equal to derivative of outer function at this point times derivative of the inner function. Okay, and don't forget that s is 1. This is expectation of eta. Generating function at 1 is 1. Derivative at point 1 is equal to expectation of Xi. So we arrive to the following formula and we conclude the proof. There will be one problem for homework. Calculate variance of this. And please be careful. This is not expectation of Xi times variance of eta. So you may think like this, okay, what is the variance of sum? Sum of variances. So take variance of eta, and what is the average number of someone's expectation of expectation of Xi. But this is not true. There is one more term here. Okay, so we studied generating functions. We see that they're useful. Sometimes you can calculate distributions, prove some properties. It's easy to calculate expectations, variances, sometimes for complicated models. And now we will study certain problems for random walks. And the first problem is this. We consider the random walks as Xi of n, where Xi is +1 with probability p. We start with the simplest example. Xi is -1 with probability q, which is 1 minus p. Assume that this random walk starts from a point x And okay, let's sigma 0 be the first time when the random walk hits 0, is infimum of k such that s psi of k is equal to 0. Okay. X plus xi1 plus xin. The problem is find distribution of sigma 0. Well, actually, we know how to do it. We discussed this a week ago when we applied undress reflection principle. Today, I'm going to calculate generating function of the distribution of sigma 0, and we will see that this generating function can be easily calculated. So let me denote by lambda n, lambda x of s, the generating function. So sum n from 0 to infinity, probability that sigma 0 is n times s to the power n, and this point x, this subindex x, means that random walks start from x. Let's consider the case that x is natural number, or non-negative integer, and let's try to calculate this. And let us make the following trick. At first, consider the level x minus 1. And divide, and then let's say that this event, that sigma 0 is n, may happen in the following way. So you walk, then once you arrive to point x minus 1, and assume that this happens at point k. Then you continue your random walk, and you arrive to 0 at the first time after n minus k steps. So probability that sigma 0 is n is equal to sum of probabilities k between 0 and n, probability that the random walk at first hits x minus 1 at instant k. Oh, maybe it is better to make the following definition as y is equal to the first instant when you visit y. Probability that sigma x minus 1 is k, and sigma 0 is n. So you walk, you are here, and now apply Markov property that says that future of the random walk depends only on the position in the current instant of time and is independent of the past. So this probability is equal to sum of probabilities, probability that sigma x minus 1 is k, and now you start from point x minus 1 and n minus k steps, so you reach 0 in n minus k steps. Well, another observation. The distribution of amount of steps from x to x minus 1 is equal to the distribution of amount of steps from 1 to 0. You just reach the level that's which is less than initial, and the difference of levels is 1. So this probability is equal to sum k from 0 to n. You start from 1. Sigma 0 is k. Sigma 0 is n minus k. And what is this? Observe that this is convolution of two sequences. And we know that generating function of a convolution is equal to product of generating functions. So generating function of this is equal to product generating function of lambda 1 of s times generating function of, and here you start from x minus 1. So x minus 1 of s. But you may continue. Sum of this two indexes is s, so you can write lambda 1 of s and apply the same calculations for lambda x minus 1. So lambda x 1 of s times lambda x minus 2 of s, and so on and so forth. And conclusion is the following, that lambda x of s is equal to lambda 1 of s to the power x. Now I will denote lambda 1 just by lambda. So the formula is lambda x of s is equal to lambda to the power x.
So sorry, and we will have in the end lambda 0, which I suppose is 1, but
if you consider this lambda 2 of s, you have just lambda 1 times lambda 1, and you stop.
Okay, sorry.
And by the way, you are right. This is a nice observation that if x is 0, if you start from 0, then you immediately reach 0. Then, so if x is 0, then sigma 0 is 0 with probability 1. And in this case, lambda 0 of S is just 1. Is just 1. Actually, this formula is true for x is 0. One moment. X is greater than or equal to 0. So this is important. If x is negative, then you do the same calculations, but you have to consider lambda of lambda to
The
the
absolute value.
to the power absolute value of x, and lambda will be like the first instant when you reach 0 from -1. We will discuss it a little bit later. Okay, we have this formula. So we need to calculate lambda of S. Okay. So we start from lambda. So lambda of S is equal to some probability that sigma is n is equal to probability that sigma 0 is 0 plus probability that sigma 0 is 1 times S plus probability that sigma 0 is 2 times S squared plus etc. And now questions. Oh, okay. I wrote the answer. This
me.
probability is 0. So in 0
But
steps, you cannot reach 0.
so we have lambda of 1 written in the first, where do we have sum? Yeah, so we have to add S to the n somewhere.
Here?
No, I mean lambda of S equals to
Yes, sure. Yeah. Thank you. Please correct me if I make mistakes. S to the power n. Sure. Okay. This is equal to 0. And now let's calculate the second term. Vadim?
we start from 1, and it's the probability that we reach 0 at the next step. Yeah, so this is just Q.
Yes, this is just Q. Exactly. So you must reach 0 in the first step. Okay. By the way, and what is this?
0.
0. Yes, 0 because, okay, you cannot reach 0 in 2 steps. And assume now that n is greater than or equal to 2, and let's calculate probability that sigma 0 is n. So if n is greater than or equal to 2, then the first step must be up. And then you make n minus 1 step, and you return to 0 at the first time. So first step is up, so p times you start from 2, you apply Markov property, and sigma 0 is n minus 1. Okay, and now let's plug this here. So we obtain the following equality. Lambda of S is equal to QS plus P probability that sigma 0 is n minus 1. So not 2, but 1 times S squared plus. So I don't think I just plug this formula here. Probability we start from 2, sigma 0 is 2 S cube plus P probability that sigma 0 is yes, no, here is 2s to the power 4th plus so on. And now please tell me, what is this? So let me write like PS, and then S plus probability that sigma 0 is to S squared plus probability that sigma 0 is 3S cubed plus so on. What is this?
So this is almost a generating function.
Yes.
For
This-
so it's almost lambda x, but
Lambda 2
minus
s.
1,
Yes, lambda 2.
lambda 2. Mhm.
Well, to write lambda 2, we need to add the probability that sigma 0 is 0, but this probability is 0.
Mhm. Yeah,
So
okay.
this is lambda 2.
Mhm.
And lambda 2 is just lambda to the power just lambda squared. And we obtain square equation. Equation. Okay. And okay. So let me rewrite it. So PS lambda square of S minus lambda of S plus Q of S is 0. There are two roots. So 1 plus and minus square root of 1 minus 4 PQ S squared over 2PS. And the question is plus or minus? So we know that generating function is analytic function in -1, 1. So it's well defined, is continuous, it's infinitely differentiable, and so on and so forth. Look at the denominator. So if S is 0, then you have 0 in denominator. So its function is analytic only if numerator is 0, if S is 0. So lambda of S is equal to 1 minus square root of 1 minus 4PQ S squared over 2PS. So the limit of this expression should not be infinity if S goes to 0. So we know that we cannot write plus. So we write minus, and if you multiply by conjugate 1 plus square root of this, then and make certain simplification, you will see that S cancels out, and this function is well defined for every S between -1 and 1. Okay, so this is the answer. This is the answer, and we know that we can calculate lambda to the power x, and okay, homework is recall Taylor expression for 1 plus x to the power alpha, and here we have square root of 1 plus minus 4pq s squared. So you may write Taylor expansion for this and calculate probabilities and so on and so forth. And the first corollary, okay, example. Okay. Example. Let's calculate probability that you start from point X and that you reach 0. Theoretically, if p is greater than 1/2, then you have tendency to go up. So theoretically, you may go to infinity and never visit 0. Okay, what is this? This is probability that you reach 0 in one step, or in 0 step, plus probability that sigma 0 is 1, plus probability that sigma 0 is 2, plus so on. And this is just lambda of x at point 1. So we have to plug this expression, plug 1 here, and raise to the power x is 1 minus square root of 1 minus 4pq over 2p to the power x. Now x is non-negative. Recall that q is 1 minus p. And we see 1 minus 4p plus 4p squared to the power x. And what is square root of this? One minus 4p plus 4p squared. Can you simplify?
It's 1 minus 2p to the square, so it's 1 minus 2p.
Modulus.
Absolute value, yes. Yes, don't forget about this. And if p is greater than 1/2, then this expression is equal to, so if 2p is large, then this modulus is 2 pi minus 1. Yes, and the answer is 2 minus 2p over 2p. We divide by 2, 1 minus p over p is q over p. And if p between 0 and 1/2, then modulus of this is 1 minus 2p, and the answer is 1 minus 1 plus 2p over 2p is 1. So the answer is to the power x, sorry, to the power x, to the power x. So this is the answer. This is
Sorry. If p is big, we need to change the sign. So 2p have be with sign plus.
1 minus 2p minus 1 over 2p is equal to 1 minus 2p plus 1 over 2p.
Yes, okay, sorry.
So sometimes I make mistakes, so please ask if there are questions. In this case, I didn't make mistake. Okay, and if you have this, you can calculate expectation, for example, if p is less than 1/2, and similarly, you can calculate generating function if x is negative, just replace P with Q and Q with P. And we will discuss the applications of generating functions for investigation of random walks next week. Okay, that's all for today. Thank you for your attention.
Thank you very much for the lecture.